Hello everyone. Today I will present you our new article entitled Forecasting Virtual Machine Resource Utilization in Cloud Computing, a Hybrid Artificial Intelligence Approach. As you know, cloud computing platforms are essential in today's IT infrastructure, providing vast resources and services such as computing power, storage, and bandwidth to customers on demand. These platforms offer scalability and dependability to ensure that the quality of service requirements outlined in service level agreements are met, making use of virtualization to optimize resource allocation and efficiency. Within these infrastructures, CPU capacity, memory, and disk utilization are indispensable for deploying any application in the cloud. So failure to manage and utilize these services efficiently can result in escalating costs. So optimizing virtual machines is very important to ensure peak performance and optimal resource utilization. This optimization is also important for cost effectiveness, as already mentioned, but efficient resource management in cloud environments remain a significant challenge, as over-provisioning or under-provisioning of resource can lead to unnecessary costs or degraded performance. So, accurate forecasting of virtual machine resource utilization is crucial for optimizing resource allocation, reducing operational expenses, and ensuring compliance with service level agreements. Various research efforts have focused on predicting virtual machine resource usage in cloud environments. So here we have a table that provides various research and efforts that have made by many authors. So for instance, the first authors, Davy and al., focused on resource management within infrastructure as a service environments. It emphasizes the importance of effective resource management to meet demand as it arises. Especially, the study explores the role of predicting CPU and memory utilization in cloud resource provisioning. So, to achieve this, the study proposed a hybrid ARIMA artificial neural network model for forecasting future CPU and memory utilization. The hybrid model combines linear components detected by the ARIMA model and with nonlinear components identified by the artificial neural network. So, by leveraging the residuals derived from the ARIMA model, the ANN enhances the recognition and amplification of nonlinear patterns in CPU and memory utilization traces. This approach enables the prediction of resource utilization patterns by considering both linear and nonlinear components, providing valuable insights for resource management in cloud environments. Then we have View and al. They've developed an adaptive hybrid prediction scheme based on auto-regression for forecasting CPU load in computational grids. So the hybrid models merge ARIMA and ANN techniques and have shown superiority in forecasting CPU and memory usage. Regarding the third authors, by and all, so they proposed a hybrid deep learning model, BGLSTM, which combines bidirectional LSTM and grid LSTM for predicting workload and resource usage in cloud systems. Their approach effectively captures bidirectional dependencies and time frequency domain features, leading to improved prediction accuracy. They applied Savinsky-Glory filter to smooth the data and tested the model on Google cluster traces. So the results showed that the proposed method outperformed traditional methods or models like ARIMA and other deep learning models such as standard LSTM and SVM, particularly in long-term prediction. Also, the other authors, which are Banerjee and al., propose a framework for improving resource utilization and energy efficiency in cloud data center through a multiple step ahead CPU workload prediction approach. The framework leverages machine learning techniques to predict the future CPU resource consumption of virtual machines based on historical data. A sliding window approach is employed to manage the time series data, and a retraining mechanism is implemented to maintain prediction accuracy over time. So, the predicted CPU workload is then used to optimize the placement of virtual machines on physical machines, leading to a significant reduction in energy consumption and improved resource utilization. Then we have Yaft and al. So they introduced a predictive analysis using deep learning technique, especially LSTM, to forecast future service loads in time series data. Their study employs this analysis to allocate the appropriate number of containers for running applications, effectively managing workload fluctuations. Additionally, their model implements a hybrid approach of vertical and horizontal elasticity to ensure efficient resource allocation and scalability. So there are so many research that have been presented in our article. So actually you can have all the information in our paper. Well, actually, in the context of virtual machine resource utilization prediction, in the context of virtual resource utilization prediction, existing research debates the relative effectiveness of linear versus nonlinear methods, while some studies suggest that statistical and linear model outperform ENN, particularly when strong correlation exists between independent variables. Others argue that artificial neural networks are more effective in capturing complex nonlinear relationships. Given these constructing perspectives, hybrid models have gained attention in time series forecasting as they combine the strengths of multiple approaches, so minimizing the risk of errors associated with relying on a single method. So, building on this foundation, our study proposes a novel hybrid forecasting model designed to predict CPU, memory, and disk utilization in cloud computing environments. Unlike previous models that primarily focus on a single resource type or two, our hybrid approach integrates the capabilities of ARIMA for temporal patterns recognition, linear regression for identifying linear relationships, and LSTM for modeling complex sequences and dependencies. This integration is intended to provide a more holistic and accurate solution for resource management in cloud environments adaptable to varying workload patterns. Well, the proposed hybrid model is designed with adaptability, making it applicable across various branches of cloud infrastructures. This adaptability not only optimizes resource allocation but also lays the groundwork for future applications in virtual machine placement strategies, an area critical for enhancing cost efficiency and overall performance in cloud data centers. So, to establish a robust methodology for forecasting virtual machine resource utilization, including CPU, memory consumption, and disk usage, we begin by allocating performance metric for a range of virtual machines using Amazon Web Services. In this setup, three distinct virtual machines were created, each running different workloads. The resulting metrics are stored in a CSV format with an Amazon Symbol Storage Service S3. Well, Spark AWS Glue with Spark was used to execute essential processing tasks on the accumulated data to ensure its quality and consistency. Following the processing phase, the refined data was stored in a dedicated S3 bucket specially designed for processed data. At this preparatory stage, the architect employs our proposed hybrid model on the processed data to forecast future resource demands for virtual machines. Well, hybrid model that integrates actually ARIMA, linear regression, and LSTM combines the strengths of each method and creates a robust forecasting framework. In this hybrid approach, each model independently processes the same input data, generating its own set of predictions for CPU, memory, and disk utilization. The outputs of these models are then integrated through a weighted averaging method where the final prediction is computed as a weighted sum of the individual model predictions. The weighted assigned to each model's output were determined based on their performance during a validation phase, where each model was trained on 80% of the collected data and validated on the remaining 20%, while the accuracy of each model was evaluated using the mean absolute percentage error MAPE, and then to evaluate the performance of the proposed model, we trained our collected data using linear regression, ARIMA, LSTM independently, and also with our hybrid model, and then we compared the result by calculating the accuracy of each model using the mean absolute percentage error. So this figure illustrates a comparison of the actual data with the predictions generated by each model, focusing on selecting extracts of CPU, memory, and disk utilization data where, well, figure A illustrates the CPU usage estimation, B shows the memory usage estimation, and C presents the disk usage estimation. So actually this figure shows that the hybrid model consistently provides predictions that are closer to the actual data compared to the individual models. This finding confirmed the hypothesis that integrating different models can lead to superior performance. Well, for more details, we will explain more details actually in the next slide. So here we have a clear comparison between ARIMA, linear regression, LSTM, and the proposed hybrid model. So for memory utilization, the hybrid model achieves an impressive accuracy of 98%, significantly outperforming LSTM, ARIMA, and linear regression. This high level of accuracy indicates that the hybrid model effectively captures the complex patterns and dependencies inherent in memory utilization data. Similarly, in the context of disk utilization, the hybrid model excels with an accuracy of 99.53, surpassing LSTM, ARIMA, and linear regression. The robustness of the hybrid approach in forecasting disk utilization highlights its ability to integrate and enhance the strengths of individual models, making it particularly effectiveness for data with both long-term dependencies and short-term fluctuations. However, in predicting CPU utilization, the hybrid model achieves an accuracy of 89.50%. While this is the best performance among the models tested, it is notably lower than the accuracies achieved for memory and disk utilization. These results could be due to the inherently complex and volatile nature of CPU usage pattern, which may involve sudden spikes and drops that are more challenging to predict. This finding suggests that future refinements in the model, such as incorporating additional features or refining tuning the existing parameter, may be necessary to better capture the nuances of CPU usage. Finally, in this study, we introduced a hybrid forecasting model that merges ARIMA, linear regression, and LSTM techniques to predict virtual machine usage in cloud computing environments. So by combining these methods, our model achieves good results, so superior forecasting accuracy and adaptability across various time patterns, effectively capturing both short-term changes and long-term trends in CPU, memory, and disk utilization. So our experiments demonstrate that the hybrid model outperforms individual models, providing more accurate and reliable predictions. Looking forward, future work will focus on refining and optimizing the hybrid forecasting model by exploring alternative architectures, fine-tuning hyperparameters, and incorporating additional features or data resource. We also plan to extend our predictions to include energy consumption, addressing a critical challenge in cloud computing. So by doing so, we aim to contribute to the development of more energy efficient cloud environments, which is increasingly important in the context of sustainability of cloud computing. And if you have any question, please don't hesitate to contact us. Here you have all the information and our emails. And thank you.